Hi, welcome to the second lecture in Unit 2, Sculpturing the Earth's Surface. In this lecture we'll be discussing running water and groundwater, two very important aspects of the systems and various processes that shape the Earth's surface. Remember, the generalized or general geologic term for the shape of the Earth's surface is geomorphology. So if we use that term in this lecture, you'll know what it means. Before we talk about the morphological controls of or how water controls morphology, we'll talk about water in general. Water exists in the Earth system as or can be viewed as a system. Oftentimes we refer to it as the water cycle or the hydrologic cycle. Water cycle, the hydrologic cycle, is comprised of five main components: precipitation, or the movement of water from the atmosphere to the surface Earth as either liquid or solid water. Skipping down to, in this graphic, infiltration and runoff. That is, infiltration is when surface precipitation percolates or moves inward into the surface of the Earth's surface between the pores of soil and rock that exist. Runoff is when that precipitation moves as surface water or stream flow across the surface of the Earth toward either a point of collection, a river, stream, lake, lake or ocean, or whether it infiltrates eventually. Evaporation and transpiration are two processes that move gas or move water from the hydrosphere or the geosphere to the atmosphere. Hydrologic cycle, in a graphical sense, is represented here, and it shows the different components of the hydrologic cycle. These types of cartoons, as earth scientists often call them, or sketches, are often very, very useful for showing complicated cycles. You'll see these for the global carbon cycle, the global nitrogen cycle, climate cycle, ocean organic matter cycle. There's lots of different cycles represented in the Earth system or contained in the Earth system, and cartoons are oftentimes, or graphical representations are oftentimes the easiest way of illustrating their various members or components and processes. In this case, we have the major component of evaporation, we have precipitation, and we have runoff. The minor component of evaporation and transportation and infiltration are represented here. What's interesting about this graphic is that it actually shows magnitudes, or shows the amount of material, amount of water that is moving from one regime to another. Evaporation from ocean to atmosphere is roughly 320,000 kilometers, cubic kilometers of water. That's a lot of water. Does not give a time scale, however, which is a poor aspect of this graphic. But it does show that this evaporation from oceans to atmosphere is much greater than evaporation from the land surface, evaporation and transpiration combined from the land surface, which is only 60,000 cubic kilometers. You get a sense of that precipitation from atmosphere to land at 96,000 kilometers. Cubic kilometers is much smaller than precipitation from atmosphere to the ocean system, which is almost 3 times that at 284,000 cubic kilometers. Running water is oftentimes characterized, is characterized by, when we talk about running water, I should say, we often think of it in terms of drainage basins. That is, areas that are defined by defined as areas that contributes water to a river system. That is, when water falls in an area, it tends to stay in that area until it moves out, which sounds a little bit silly, but in a way it's useful, especially when we're talking about how water impacts the Earth's surface. Drainage basins are essentially zones where water is collected and transported that are isolated from other zones. Divides are what separate drainage basins. This schematic or cartoon of a drainage basin shows it quite simply, and that is when water falls anywhere within this dotted line. Precipitation occurs anywhere within this dotted line, whether it's snow or liquid water as rain. It's going to drain inward through the system of tributaries, through the system of stream transports to a central stream or to a series of centralized streams that eventually move that stream flow or move that liquid water to its outlet. Whether this is a lake or a bay or an ocean, doesn't really matter. It goes to an outlet. On a micro scale, that is a small scale, you can see what a divide looks like. Basically, it's the highest point between two areas where if water were to fall on one side or the other, it would go one way, or if it were to fall on this side, it would go the other way. And that moves through naturally developing rills and gullies. Stream flow is how scientists describe the movement of water over the Earth's surface. Stream flow is characterized by velocity, discharge, which is volume, and gradient. So factors that determine velocity are the gradient of a stream, that is how steep it is. Higher up on, you can imagine that higher up on mountain ranges or hills, you're going to have steeper slopes. When water is moving along a flatter surface, where the slope is lower, velocity is probably also lower. Velocity is controlled by channel characteristics, shape, size, and roughness, and also the discharge, or the volume of water flowing in the stream. Stream flow always occurs down gradient, that is, from higher elevations to lower elevations, and can be described by hydrogeologists or earth scientists in terms of what's called a profile, a stream profile. That's a cross-sectional view or a sideways picture of that stream, oftentimes on a graphical piece of paper. It's not really an illustration of a stream, it's more as a plot of the different aspects of that stream. Stream profiles go from the head or the source to the mouth or the outlet. Profiles a smooth curve and is characterized always by, well, in general terms, gradient decreasing from the head to the mouth or the source to the outlet. Factors that increase downstream. Velocity, this is incorrect. Velocity actually increases, velocity is higher upstream. Discharge occurs downstream. There. Channel size typically increases downstream as more water is moving, as sides, tributaries, and streams add water to a stream channel. The discharge will increase, and usually the channel size will increase proportionately. Factors that decrease downstream, gradient or slope decreases, and gradient or slope controls velocity. So and channel roughness, as more water moves through, the erosional capacity of that water increases, and stream channels are typically much smoother. This is what a sort of stream profile looks like. This profile is representative of, say, for example, a profile from a source of a stream at the top of Mount Whitney in the high Sierra Nevada, high mountain range in California, central California. As that stream goes down slope cutting through these valleys, other streams adding to it, adding water, the volume of water gets bigger. The velocity, as it gets less steep down here in the foothills and eventually out on the plain, the velocity slows down. So up here we have the head, where steepness or slope is the maximum, and velocity is at a maximum as well. We'll see this in a little bit again when we talk about what the streams can carry. As that stream starts to get into the foothills and the mountains are less mountainous, for lack of a better term, that stream profile shallows out, slope gets reduced, and the velocity is lower, even though the discharge or the volume of water moving through the system is higher. And eventually it reaches the end or the mouth or the outlet, where stream flow is at its maximum discharge, unless something is taking water out of the system, like agriculture or other things. It reaches its maximum output, maximum discharge, but its lowest velocity. Running water does a lot of work, has a tremendous impact on the surface morphology of the earth. Streams are major agents of erosion, which we looked at in the last chapter, and major agents of transportation of that eroded material downslope due to gravity. Transported material in a stream is called load, and you can have three different kinds of load, or streams have three different kinds of load. Dissolved load is exactly that. It's the components of rocks that are dissolved in the streams in water. Those you can't see because they are dissolved. It's a minor component by mass, but can be significant in impact. Suspended load, although I should say that dissolved load is one of the most important factors in terms of determining the ocean salinity, as well as the balance and the distribution of elements around the globe. Suspended load is material that is small enough for a given stream's velocity and capacity. It's small enough to remain kind of suspended or entrained up in the water zone, in the stream flow zone of a stream. Whereas bed load is material that is too heavy or for whatever reason is unable to be carried along smoothly by the stream and is instead rolled along the bottom. It bounces and rolls and tumbles downstreams. You can imagine that's larger material typically. Load, stream load, is related to a stream's competence and capacity. Competence is the maximum particle size that a stream can carry, and clearly it would relate to where that stream is in the profile and the velocity. Now, the velocity is highest in the upper regions where the slope is the greatest. So competency is highest up here as well. So that's where larger grains, cobbles, pebbles, boulders even, and gravel can be carried at least as bed load by a stream. Further down in that profile, where velocity is lower, the competency of that stream will also be lower. That is, finer material will typically be carried along. The capacity is the maximum load, that is, how much mass can be carried. So competency is related to velocity, and capacity is related to the volume. Basically, how much water is moving will determine how much material can be moved. Streams not only erode and transport, but they also deposit material. Deposition usually occurs in areas where stream velocity is decreasing, typically in the lower regions of a profile. Competency is reduced. That is, the maximum size of particles goes down as velocity decreases, and as a stream's velocity decreases, as the slope steepness decreases, then clearly you're going to drop out material. Sediment begins to drop out as stream velocity decreases. Stream sediment, known as alluvium, is characterized by well-sorted deposits. Sorting is the geologic concept of how unique or how defined it defines it, or it's a characteristic that describes the distribution of grain sizes in a deposit. That is, if something is all sand, it is considered well sorted. And remember, we're talking about sand as a specific and very, very precise size fraction of sedimentary material. If a sediment or if a deposit is all clay, or 90% clay and 10% silt, it would also be considered well sorted. Most of those particles are of a similar grain size. However, if a deposit were 40% gravel, 20% sand, 20% silt, and 20% clay, you're going from clay, very, very fine particles, all the way up to gravel. That would be not a well-sorted sediment. That has a big mixture of grain sizes. Stream sediments, or alluvium, tend to be well-sorted because as the stream profile shallows out and stream velocity drops down, only certain size fractions, starting with the biggest first, only certain size fractions drop out, and you'll get deposits that are characterized by a single size fraction. Depositional features of streams include deltas, which often occur at base level, that is, where outlets are, either in streams coming into lakes or oceans. Natural levees, which form parallel to stream channels and are essentially coarse material built up on the edges that increase the height or the depth of channels. And areas behind levees may contain swamps or other tributaries that are essentially depositional features of streams. This graphic shows how natural levees form in a floodplain or a low stream flow environment, or high discharge but low velocity environment. Typically, you'll find in floodplains where slopes are very, very low, so you'll find what are called meandering streams. That is, streams that kind of wander back and forth and are characterized by slow-moving, high discharge, relatively high discharge water. When those areas like that flood, you can see down here, you can see the tracings of those meanderings of that stream channel that is up here. But water overtops those edges, those channels, and can spread out over the entire plain. From a cross-sectional view, what is happening is, as that water overtops those channels, it brings up coarse material and leaves it on the edges. As those floodwaters receive, the stream channel is actually slightly higher. If those repeated cycles of floods continue to occur, more material, additional material gets added onto that levee. Eventually it builds up to the point where that channel is significantly deeper and won't flood as often. It will still flood, but won't flood as often. Base level is a concept in stream flow where the stream can no longer erode below. What you can often think of that as is essentially its outlet, wherever the stream stops moving, either coming into an ocean or a lake, and it can be the ultimate base level or the final base level, which is sea level, because streams don't flow lower than sea level, or it can be a temporary or local base level caused by either a lake or some other change in the stream flow characteristics. When that base level changes, it changes the distribution and the manifestation of depositional and erosional environments. So modifying streams or modifying how they flow can have far-reaching consequences both upstream and downstream. This graphic shows how changing base level typically occurs, or how a base level can be changed. In this top graphic, which is an unaltered stream system, you have dendritic drainage pattern draining into streams, just kind of tributaries joining up, higher velocity up here in the steeper zones of the profile, lower velocities but higher discharge, and you can see these meanders down here, which are characteristic of very low velocity floodplain type streams, culminating in a delta at the outlet. And that delta is a place of deposition where stream erosion no longer can occur, and instead you get deposition because you're at base level. That's the definition of base level. It's where erosion no longer occurs. In this bottom graphic, you see instead a dam and a reservoir is built up midway through or midway up that profile. And what you get here is you actually get a zone where you're no longer, the original profile is down here, but because the stream is approaching its base level and erosion can no longer occur and deposition instead starts to take place, you get deposition of deltaic type deposits, just like you do up here, but instead you get them higher up that profile. And that's because we have a new temporary or local base level. Now again, that same process happens down here when that water is released, and you get your final ultimate base level down at the bottom. Running water or stream flow oftentimes exhibits or introduces a characteristic shaping of valleys. Valleys are divided into two types. You can get narrow valleys and wide valleys. Narrow valleys are characterized by downcutting, or basically water moving very fast, causing a lot of erosions, whereas wide valleys are characterized or are caused by more depositional aspects of stream flow. So in narrow valleys, they're typically V-shaped. Active erosion is taking place as streams move down toward base level. Often include rapids and waterfalls, areas of high velocity, high base load, high suspended load, and reasonably high dissolved load waters. Whereas wide valleys happen where a stream is near a base level, either a temporary or an absolute base level. Downward erosion is less dominant, although you do get erosion. It's just not downward oriented. It's oriented from on a lateral or side to side aspect, and that's because you can imagine here, as this graphic shows, that as water moves through these meanders, water that is on the outside edge tends to move faster than water that's on the inside edge. And that's because the water on the outside edge of this curve has to actually move a greater distance than the water on the inside edge. When water is moving on the outside edge faster, it tends to, velocity is increasing, and that's when erosion takes place. When water is moving slowly through the inside edge, that means capacity and competence are dropping, and it's actually depositing material. So oftentimes in wide valleys, you'll get these meandering floodplain or meandering streams where you have inside of the curve deposition and outside of the curve erosion. And that can introduce some or develop or result in some pretty interesting features that are pretty characteristic of wide down profile stream environments. It's so interesting, in fact, that you can develop what are called cutoffs and oxbow lakes. Basically, what you have here is a situation where, as water is coming through the stream, it's depositing on this inside lobe and it's cutting around the outside of that stream. Eventually, it may cut so much that it cuts right across this little berm, and this part of the river all of a sudden jumps right into this part of the river. And what will happen then, as this body starts to increase depositionally, is that it will create a bridge of land right in there, and this part of the river all of a sudden becomes cut off. It no longer becomes part of a river. It's called an oxbow lake. It's basically a cut-off lake. And that's what these features are down here. These were original meanders right there. They came in right there, but they've been cut off by these features and are no longer connected to the river system and are in fact oxbows. And you can oftentimes see those if you're flying across the country in an airplane. You can look down in the Midwest, and you'll oftentimes see, especially in the southern Midwest, you oftentimes see lots of meandering rivers with oxbow lakes. They're very characteristic of wide valley floodplain environments. This is an example of a meander loop in the Grand Canyon of the U.S. Meander loops don't always occur in low elevation floodplains. They can also occur at relatively high elevations. What really controls them is the velocity of the stream that ultimately produces them. Lower velocities tend to meander and eventually cause cutoff and oxbow lakes. Drainage patterns of water systems are often characteristic or literally controlled by the earth underneath those systems. Typical drainage patterns are dendritic, radial, rectangular, or trellis, and those are all caused by various geologic subsurface features. Dendritic patterns are often characterized by relatively uniform bedrock, and they're chaotic in nature. That is, this is a fractal geometry or fractal pattern where smaller scale structure actually mimics or reflects larger scale structure, or vice versa, however you like to think about it. But because there's no underground or there's no, the relatively uniform bedrock doesn't necessarily influence the direction of water flow. Chaotic water flow exists where it doesn't take much for a water stream or a tributary to form and kick off or go a slightly different direction than it otherwise would. And so you get these kind of unpredictable patterns, dendritic drainage. If underground bedrock has a particularly systematic pattern of jointing or fracturing, it can often manifest itself on the surface as surface features of control the pattern of drainage. This example is relatively simplistic in that the bedrock underneath is fracturing in a right angle pattern. Therefore, you get drainage pattern that is characterized by right angle turns. Similarly, in bedrock that is uplifted and stressed and potentially overturned or folded and faulted, you can get differential patterns of erosion that may interact with certain layers much more and erode certain layers much faster than other layers. And you can have patterns of drainage that follow along fault planes, bedding planes, or erosional features. And lastly, a common method of, or a common pattern, drainage pattern, is from volcanic or cone patterns of mountain building, where water that falls near the top will drain radially off on all sides. Floods and flood control are where most people pay particularly close attention to running water systems, and that's because floods are the most common form of geologic hazard. Weather oftentimes influences or controls the magnitude and intensity and frequency of flood systems, but human beings have the ability to interfere with stream systems in a way that can either augment or mitigate the risk of floods. Human efforts such as building artificial levees, flood control dams, or channelization can oftentimes, in some cases, worsen the impacts of floods in areas that aren't protected by these engineered protections. But they can also improve or decrease the consequences in areas that do have them. And non-structural approaches such as development regulations, encouraging critical infrastructure to be flood resistant or not flood vulnerable, can oftentimes improve the consequences or reduce the consequences of floods. This graphic is a satellite view of the Mississippi and Missouri river systems where they join, and it will blow it up in a second, and you'll see many characteristics of stream flow, oxbow cutoffs, dendritic drainage patterns. We see some channelization and channel depositional areas, erosional processes. This blow up shows you can see more dendritic systems, oxbow cutoffs here. You can see erosional aspects along the levees or the natural along the sides. You can also see areas where there's obviously some levee protection, and that is channelization, where the river channel is much thinner than it naturally would as reflected upstream. Now, the other aspect of water near or at the Earth's surface is groundwater. Stream flow is characterized by water on the surface, whereas groundwater is water that is deeper within the Earth, but still within reach, so to speak, of human beings. It is the largest freshwater reservoir for humans, but as an erosional agent or a geologic agent, it is not that significant, other than with sinkholes and caverns. Water with high dissolved CO2 or carbon dioxide tends to be acidic and can erode significant amounts of geologic material, to the point where underground caves form, or even sinkholes, which are of particular interest in Florida. Groundwater can also act as a buffer or a storage system for rapid changes in stream flow. And that's because the water table will often intersect, or the zone of saturation in groundwater will often intersect a stream bed, and can either add or take out water from a stream to either accommodate increasing flow during flood stages, or add water to mitigate decreased flow during droughts. Water beneath the surface is characterized or described with two different zones. There's groundwater is distributed in two zones: the belt of soil moisture, or what's called the zone of aeration, or the unsaturated zone. That is where pore spaces in the ground are filled mainly with air, but there is water adhering to individual grains and organic matter. And then there's the zone of saturation, where all pore spaces in the material are filled with water. And water within this zone, or between those pores, is considered groundwater. Water table is the interface between groundwater, or the zone of saturation, and the zone of aeration, or the interface between the saturated zone and the unsaturated zone. Features associated with subsurface water and this are shown on this graphic, and are quite numerous. We'll start from the bottom up, and that is the saturated zone, where water. This graphic kind of shows that water fills the space between all the pores of grains, is separated from the unsaturated zone, where some water is between the pores, but air is also between the pores. The zone of saturation and the unsaturated zone are separated or defined by what's called the water table. We can see how that water table intersects this stream right here, and can either add water or take water away from that stream in kind of an equilibrium type of situation, or a balance between the two systems. You'll notice that not all saturated zones have to be below unsaturated zones. An aquitard is a layer of impermeable rock that water cannot go through. So if you have a layer of geologic strata, or a geologic material that is impermeable to water, and it is kind of doesn't spatially just go far and wide, it can kind of trap a layer of saturated zone, or an aquifer, on top of it. And this is called a table aquifer. Underneath it, you can have unsaturated rock, as long as there's a layer, or a kind of a catch pan for that saturated zone. Wells that are coming in from the surface have to penetrate to the saturated zone in order to draw water. This is an example of a well that would not give any water, because there's air in between all those pores, and it's just not going to draw any. Whereas this water that goes down into this perched water table would be successful. It would produce water. And springs are areas where water naturally seeps out of the ground, emanates from the ground, and those are usually where water tables intersect a surface of an outward surface, and a soil surface. It's where a saturated zone protrudes out, or intersects the land-air surface. Water beneath the surface is characterized by a couple different aspects. Distribution of groundwater is controlled by porosity of the subsurface, that is, the amount of pore space. It's often given in as a percent. It determines the amount of groundwater that can be stored. And a concept called permeability is related to porosity, but what it is, oftentimes people use these terms interchangeably, but they are different. Porosity is literally just the amount of space that water can exist in, whereas permeability refers to the ability for that zone to transmit water, for the ability for water to move through it. So it's more a rate of movement than a volume or a percentage. An aquitard is a impermeable layer of material through which groundwater will not percolate. So aquitards are impermeable; their permeability is 0. And an aquifer is permeable; that is, water can move through it, and it's oftentimes characterized by a porosity, that is, a volume of water that can be contained in that aquifer, as well as a permeability, that is, a rate at which water can move through it. Features associated with groundwater: springs. You can have hot springs, and geysers, which are areas where groundwater is moving past a source of geothermal heat. That is, water is heated up by earth processes. Those can manifest themselves at the surface, either by pools of warm water, or by eruptions of steam and water. Geysers are characteristic of areas of volcanic activity. The Yellowstone caldera is one that's particularly famous in this country, but they exist in different places around the world, usually in areas where there is volcanic activity, either spreading centers, divergent boundaries, or convergent boundaries where there's arc volcanism. Wells are used to remove or to extract water from aquifers, or from the water zone of saturation, and often have to be well calibrated or well designed so that they do not cause the water table to drop to the point where the wells become dry. So you don't want to pump through a well at a rate that's greater than the permeability or the ability of that aquifer to transmit water. Artesian wells are a somewhat interesting example of water apparently not moving downhill, although in fact water is moving downhill or down gradient from an energy perspective in an artesian well. And that's a place where the water pressure in the ground is higher than the groundwater level, or even the surface where the well is, where the hole or the well is, and water is basically is under pressure and is able to come out of a well naturally without being pumped. When you have a well into a water table or into an aquifer, you want to pump that well always with an eye toward making sure that the well does not exceed the permeability or the recharge rate. All wells, as they pump, will create what's called a cone of depression, and that is, as water is removed, the water table drops down where that well is. The trick is to not pump to where that cone of depression drops below the bottom of the well. These are two examples of cones of depression. In this example, this third well, this deeper well, really pumps down, and its cone of depression goes so far that it causes these two other wells to lose their connection to the water table, and those are no longer active wells. So if you're ever in a situation where you're either putting in a well or you're living near somebody who is, make sure that those are designed well. Artesian systems, on the other hand, are places where water percolates at a higher elevation, percolates into a permeable layer, usually is constrained by an aquitard above it and an aquitard below it, so that water cannot percolate upwards or downwards and instead is essentially trapped. And then when you put a well in, it appears that water is moving against gravity up through the surface and is no longer flowing downhill. In fact, it's flowing uphill naturally without aid. Well, the way you really need to think about it is when that water is confined, it's essentially connected to its point of origin is up here, which is actually higher. It's where it first percolates. It's actually higher than where the well comes out of the ground. And so that artesian well will spray water out right here, but it will only spray water out. It will only allow water to go up as high as its pressure surface or the level of that water back at its point of origin where it originally infiltrated and started and began to percolate. So, in fact, this is another example of water flowing downhill. It just doesn't seem like it. It's a bit of an illusion. Groundwater has a host of potential environmental problems. And remember, environmental problems are as they relate to humans, typically in this course. Groundwater can be used unsustainably. That is, we use it, or human beings tend to use it without thinking about how it can be renewed. And with the water cycle, all water is maintained and constrained. It does not leave the earth, but it does. Its availability and suitability can change due to issues such as contamination and where it's located. Drawing a lot of groundwater through pumping and land use or for use on land can cause what's called land subsidence due to the fact that sometimes water, especially in saturated zones, water exerts hydrostatic pressure on grains, mineral grains, and actually it comprises part of the force that keeps the land intact. When you remove that water, those grains can start to settle and become closer together, and you can actually cause land subsidence or depression. Land can drop. And groundwater contamination, which is fairly intuitive. When groundwater is contaminated, it becomes less suitable for human or use by humans, whether it's in agriculture or drinking or industrial processes. The geologic work of groundwater is one of the most interesting things, although it's not incredibly important for humanity. Groundwater is often mildly acidic because it contains carbon dioxide. It's dissolved carbon dioxide that makes it a weak acid called carbonic acid, which dissolves the calcite mineral readily in limestone. Caverns are formed by dissolving rock beneath the Earth's surface, and they're typically formed in the zone of saturation. Features that are naturally found in caverns are dripstones, or in the zone of aeration, or dripstones. That is where water that is highly saturated with respect to the mineral that is being dissolved will oftentimes reprecipitate or redeposit that same mineral, and you can form pretty interesting and quite amazing structures in caves. Calcite it gets deposited as water that's saturated with respect to calcium carbonate, evaporates, and stalactites and stalagmites form from the same material that was eroded away or dissolved to even form the cavern in the first place. This is an example or a picture of in Carlsbad Caverns of stalactites from the ceiling and stalagmites from the ground up. These are formed by waters that are dripping and forming these amazing features. Karst topography is related to cavern formation, and it's typical of carbonate areas or limestone areas. It's formed by dissolving rock at or near the Earth's surface, and sinkholes and caves and caverns are characteristic of it. Same processes that form caverns form sinkholes. That is, mildly acidic groundwater percolating through an area that is significantly carbonate. That water will dissolve that carbonate and forming gaps and cavities underneath the surface, and eventually the structural integrity of that surface is compromised and things collapse. This graphic shows it better than most words do. This bedrock here is carbonate or limestone. In aquifer, in the saturated zone, you have mildly acidic water, and as that aquifer or that water table moves up and down, that mildly acidic water will dissolve different zones of that bedrock. You can form caverns, that is, areas that are big cavities underneath the ground that are not manifest readily or easily seen in the surface, or you can manifest, or those areas can be shown by sinkholes, depressions in the surface that are caused by mild collapse of the land surface above the voids. And that's the end of chapter 5. The next chapter will be chapter 6. I hope this was useful, and thanks for listening.